Welcome again to the course of mass balance. In this video, we're going to take some theory about the mass balancing, which is, in general, what is the mass balance principle? It's easy, don't worry. And actually, I'm pretty sure you already know it, is that mass or matter can neither be created nor destroyed. So that's good because then we know that matter will always be the same because it doesn't destroy, disappears, creates. The only thing we're going to see is that it's being transformed. So because we're going to see some chemical processes, we're going to account that transforming as production of a species, production of I, and consumption of a species I. So just that. That's cool, I think, because you can do an actual equation like add inlet minus outlet equals accumulation, or I don't know. If we didn't have this, we could not do the equation and it will be probably a guess. So that's cool. It's cool. We're not going to see energy in this course, not at all. Actually, many students tell me like energy and mass, they have a relationship. It's equal, actually this one. It's very famous. Here's energy, here's mass, and this is the speed of light to the second power. No, we're not going to use this because this is only in nuclear reactions. It's true, nuclear reaction is a chemical reaction, but we're not going to see these reactions in this type of process. We're going to see only chemical conversions that don't involve like nuclear chemistry. So don't worry. You want to learn more about energy, you can go to the energy balance course. But in this course, we are only concerned in mass. Okay, volume. Yeah, just go to the energy balance course if you really want to learn more about energy. And okay, what's the principle in general? Remember, the definition of a system is any portion of the universe. You choose it, but if you choose it, you need to delimit with boundaries. So let's say, in this case, I have this system. Inside, it could happen a reaction. We could be mixing. We could be splitting. We could be drying. We could be humidifying. I don't know, like many things. We could be heating. We could be pressurizing. I don't know. There's many processes that could happen to the system. And of course, if we are talking about mass or matter, you could get inside matter. For example, if you have a house, you could go inside, bring groceries, you're bringing food inside the house. And of course, you can have also outlet. If you, I don't know, take all your garbage out of the house, you're taking out matter. You go inside, goes food, outside goes garbage. And consumption will be, I don't know, if you are eating food and then, well, technically I don't want to explain that much, but there's going to be a consumption, there's going to be a production. I'm going to make an example later, further on, so you can get the actual knowledge of what is this consumption and what is this production concept. But in general, just get used to inlet, outlet, consumption, and production. And of course the system. So the mass balance analysis is going to be this red square. Make sure you get all the streams or all the flows with the square or your system, because if you do something like this and you only get this outlet, this inlet, this, you don't get it, and you get this outlet, you will be asking yourself, oh, why I am, I don't know, accumulating, why I'm getting, I don't know, if it's air. And this is very typical in engineering. You probably think it's pretty dumb, but actually you sometimes don't actually know if you are getting another stream or something is entering the oven. For example, you have a furnace, you have fire in it, and you are asking yourself, oh, why I need to burn that much if it's not that much matter. And you will get to use that there's a small stream of, I don't know, air or even water. Like water is dropping and it's cooling the wall, and that's why you need more energy and therefore you need more fuel. So it's very important to get to know the system and actually do the boundaries and get them well. Once you have the boundaries of your system well selected with all the streams going in, all the streams going out, you can worry about consumption and production. So, as I said before, this is the system. Now we want to do an actual equation. So if I wanted to know matter or how much mass is going inside the system, for example, if I have this glass of water is empty and I start filling it, I'm accumulating water. Or for the other side, if I have, I don't know, this big container and I have it full and I'm actually emptying it, and this is my system, this is my system. Well, the concept of accumulation is how much matter per time or unit time are you accumulating, or I don't know, like not accumulating. So this will be done with these four concepts: inlet, outlet, production, and consumption. The inlet is here, as I told you, and we could have many inlets anywhere. It doesn't have to be right or down. You could have many outlets, actually an arrow just going out of the system. Also, you could have it everywhere. The concept of production, if you're having a chemical reaction, you are producing, I don't know, you have a reaction A reacts to B with a lot of temperature, then you're producing B. You are asking yourself, oh, why I'm increasing the concentration of B? It's obvious, because you're actually converting A to B. Now consumption will be, for example, if you're doing a mass balance in A, on A, you'll be asking yourself why A is disappearing, because of course it's reacting to convert to B. So either consumption and production. Hopefully you get to use those concepts and understand them. And finally, because inlets go plus, we're getting more matter. Outlet is taking out matter. Production, of course, is getting more matter. These ones are specials. I'm talking about chemical reaction. Minus consumption. This will accumulate in your system. And this is very tricky, because I know you probably are asking, I just told you before that there's no production and consumption, that we don't destroy nor create matter, but I'm talking about chemical species. If I do this mass balance, actually a normal mass balance, like kilograms, you will never have this. You will never have production nor consumption. But if we're talking about moles of A, mole is a molecule, you will have an inlet, yes, you're feeding, and you have an outlet that probably, I don't know, reacts. It doesn't react that much. In this reaction, doesn't react that much, so you have an outlet. You have a production? No, you don't have production, because it is converting all to B. So we have consumption here. So just get a little bit, this is kind of tricky. Production, consumption, just know that we're talking about chemical reactions. So of course there's going to disappear A, but it's in mass. A is actually converting to B. So 10 kilos of A will never give you 15 kilos of B or 5 kilos of B. 10 kilos of A will give you always 10 kilos of B. That's the mass balance concept. But of course in moles, you will be like, okay, 10 moles of A are reacting to form 10 moles of B, and I disappear 10 moles of A, of course. So don't get that worried. We're going to see a lot of examples, but just get to know the production and consumption are only in chemical reactions. And now let's do a simple example. I call this the city example. Inlet of people is going in, it's immigration. It will be always positive. Okay, imagine we have this city, it's so cool that many people wants to go in. 50 people are going in. I don't know, this could be per year. Actually, could be also per day. You're in a cool city, 50 persons per day sounds like normal. And outlet. We're taking out people. People actually don't like the city. They thought it was cool, but they stay there and they say, nah, I actually don't like this. So we're going to have also emigration, -3. And then of course inside, we will have inside the city people that is burning. People is being born. We have these 100 babies per year or per day. It doesn't depend on the size. And of course you will have people dying. That's sad, but we have these people which are dying or consuming themselves. The accumulation, now hopefully you get to understand what's accumulation. What will be the accumulation of the city? And this is almost intuitive. You will say how much people is, or the growth of the city, how much is it? Well, you just need to do this addition. Will be 50 minus 3 plus 100 minus 25, which I have here. And the number gives you 122. What does that mean? This means since it is positive, you are accumulating 122 persons per year, let's say per year. What will happen if, I don't know, it's not that cool, we don't have that much babies burning, and we have no immigration. Actually, it's a shitty city, we only have immigration and people is dying. We will have 0 minus 3 plus 0 minus 25, which will give you minus 28. And what does that mean? Why do we have a negative number? It means that the city is losing in general population. So 28 persons per year are disappearing. So hopefully you get the example, because we're going to go to a similar example, but now with more chemistry. So if I ask you what is the accumulation in the system, and I tell you I have inlet of A moles, or no, A kilos of A, it's 100, and I have a production of 0, I'm not producing A, let's say probably is the reaction I told you before, A is converting to B, so I have no production, and then the consumption is 50, I'm telling that these 50, I just got 100 kilos, and from these 100 kilos you are producing, you are producing 50 kilos of B, which means 50 kilos of A are consuming. The outlet, well, let's say it's 25 kilos. So it's very easy. I'm putting 100 kilos inside. The outlet is 25 kilos. So in this system, we either have 75 left. 50 are being consumed. So 50 out. So the only accumulation, also the system is accumulating 25 moles. What does that mean? It probably, with time, it will get full of A because it's not reacting, and we will have to take out those moles. So just mathematically, I show you this. The mass balance in the system is 100 minus or plus the production, which we don't have, minus 50, which is the consumption, minus 25, the outlet. Do the math and you get 25 kilograms are being accumulated in the system. So it's easy. You compare it with the seed example, the reactor example is similar. Just get to know what's the inlet, what's the production, what's the consumption, and what's the outlet. That's the actual problem. To know each and to do the math, because this is a very easy example. We're going to see more like complicated problems, so just keep reading. Now we're going to see the mass balance equation. I told you before it was something about inlet minus outlet plus production and consumption. This is very typical for chemical process, chemical reaction. But this is typical for mass balance in general. Is equal to the accumulation. And accumulation, it's always generally mass over time. So mass is accumulating in time in the system. So we do actually account how much mass is getting in this time. And what I want to show you here is that we can do it we can do a mass balance on a species. When I say species, let's say I could be any value, could be, I don't know, CO2, could be moles of A, or actually just A, could be water, etc. So we could have inlet of water, or I, outlet of I, which is, I don't know, I would choose water in this case. Production of water, if you are having a reaction that produces water, minus consumption of water. I don't know, maybe you have another reaction that has consumption. this will give you the water in the system, like how much water is being accumulated in the system. So just get used to that. We're going to see that much further in chemical reactions, but just know that we can do mass balance over species. And now we're going to see two different types of mass balance: differential and integral mass balances. Differential mass balance is essentially an analysis in one instant of time, which means one instant means as time goes to zero. We're going to use a lot of velocities or rates, for example, grams per second, kilograms per hour, barrel per day, and it's a typical process for continuous processes. So since we are very interested in these processes, this typical chemical engineering, you have plants and they work like 24 hours per year every day. So this is a continuous process. The temperature, kilos, everything, we try to have it the same. So this is a continuous process, if you remember. And the tip I use here is it's very convenient to use a time base. So I don't know, you say 10 kilogram per hour. I will say like use 1 hour, so you have only 10 kilos to analyze. You don't have to, but I do recommend it. We will use this a lot in the course. This is like 80 to 90% of the balances we're going to use. So please get to know it very, very well. Remember instant, remember it's a velocity or a rate, and it's typical for continuous processes. Now the integral one, which we're going to see only about like 10 to 20%. You're probably asking me why we're going to see this. I don't know. It's very important to do other types of balances that doesn't imply continuous processes. Actually, it's very cool because you are going to do processes in two instants of time. So you have time 0 or time 1, and you have final time. So for example, if you are, this is typical, you will tell me like, oh, why are we studying this? Maybe you're filling a tank, you have, I don't know, 10 liters per hour, and you have 100 liters capacity. You will, I don't know how to explain it, like what will be the time needed to fill the tank. And of course, like with not math, you can say 10 hours. You need 10 hours to fill 100 liter if you're flowing 10 liter per hour water here, you flow here. So that's why we use two times or two instants of time. We use quantities rather than velocities. I told you before it was velocities, but in this one we're going to use more quantities. As I told you, 10, like how much, 100 liters. I want 100 liters is punctual. Before you wanted the velocity, like what is the rate, like 100 kilograms per second. But no, now we're going to be more interested in the quantities, like kilogram, ton, pound, liter, etc. The time elapsed is very, very easy. It's just final time minus initial time will give you the change in time. It's very typical for batch processes. Actually, it's a transient process. So every batch process is a transient process. And the trouble or problem here is you need to feed, react, discharge, and you repeat the process. You need to repeat it because it's not continuous. So you do one cycle, and then you need to do second cycle, and then you do third cycle, and you continue until you get your desired quantity. Like if I'm producing 100 kilos of product and my reactor can only give me, I don't know, 10 kilos per batch, I will have to do 10 times that reaction so to get 100 kilos. And this is all, of course, the time or the reaction time involved, I don't know, this is 1 hour. If I need to do 10 reactions and I need 1 hour, you will need at least 10 hours. So you will have to probably repeat. So that was about the integral balances. Differential balances are the important ones, don't get confused. So it doesn't mean that integral is not important, but if I were to choose, if I were a student and I will say I don't have that much time, I would recommend you to study the differential mass balance. Unless you know your exam is about integral mass balancing or about transient processes, this will be the answer. Please study this. But if not, I do recommend you to study this differential mass balancing. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. So thank you guys for the support and the love.